All right, so I will be explaining structure prediction for graphical models, which is really important. And structure prediction is an always inference like the inference of some product networks are generalization of what we do for simple, for example, conditional random fields or hidden Markov models and those simple models. And it's a generalization of that, and it requires you to have a structure. For example, in chemistry we have a structure in the molecule, and or in natural language processing, which I like, we have a structure on the words and the sentence. Either you are doing dependency parsing, or you are doing complex event extraction methods that you have multiple triggers, and so it's very important. So the best book for graphical models, I mean the introductory book for graphical models, is, I think that it's the work of Bishop in Microsoft, about more than 1,000 pages. But if you look at the chapter for graphical models, you will see this beautiful equation that psi are the potential functions. This is nothing, this is just the probability, and here we are just normalizing, so z is normalization constant, or some people say partition factor. We normalize it to produce a probability. So we multiply all of these potentials in order, because a complex graph, for example, a tree is multiplication of some potentials. Because, for example, if you separate it by clicks, these clicks are, or Markov blanket in the context of Markov chains, are good separators, and they can intuitively, so they say that you have a complex function, you decompose it into a simple, so it's just the classical, so it's simple math. Just you decompose a complex, we have a function of complex variables, x1 to xn. You decompose it into simple, for example, x1, x2, a function of x1, x2, and the rest of the variables, so that you reduce the complexity of your problem. And so because we are restricted to potential functions which are strictly positive, it is convenient to express them as exponential. So when we say this is E is energy, and so in quantum mechanics, quantum field theory, all of the statistical mechanics, we always look at it like this potential. So it's energy, E is energy function. And this exponential representation in physics, we call it Boltzmann distribution. And it is really important in machine learning as well. The joint distribution is defined, as I said, it's just a product of potentials. So the total energy is obtained by adding the energies of each of those clicks, maximal clicks. For example, we start with just a simple chain, because you can visualize and see it very quickly, you get the idea. And the same idea goes for more complex or any general graph. So for inference on a chain, no matter if it is directed like A or it is indirected like B, you can define the joint distribution by just multiplying these psi 1, 2, psi 2, 3, psi n minus 1 n. So these potentials, when you multiply one, you're saying that these are independent of each other. So the probability, you could multiply this probability. Think about it like, because it's proportional to probability. And z, as I said, is just a normalization factor. So it becomes a very good probability distribution. And we want to maximize the likelihood always in statistics, or minimize the loss in machine learning. And the inference on a chain therefore becomes like this. This alpha reminds you one thing. If you have seen my lectures on conditional random fields, or any dynamic programming that we do, forward, backward, and but in the next lecture I will talking about message passing and those some product networks, some product algorithm, which is a generalization of what we do for forward backward algorithm, and many other simple algorithms. But it's just generalization of that, because we are not restricted to simple graphs. So this is, if you call this a mu of alpha and this mu of beta, then you multiply them and you normalize by z, it becomes the probability of one of them. For example, this is xn. What is the probability xn to become label number 1, label number 2, label no? Because this one could have different colors, or let's say labels. And we now give a powerful interpretation of this calculation in terms of passing of local messages. Just like in your brain, these messages are passed through the neural networks inside your brain. So it's very intuitive, much more intuitive than those high-dimensional vectors that you do in deep learning, those things. The idea is the same, but now you see that we are just passing some messages. And we are not even differentiating anything. Everything is, you can think about everything is discrete, because each node in a factor graph, each node is either a simple node or a factor node and then factor. So we are passing, I'm saying that we are passing the messages. And this is the passing of messages around the graph. So the mu of alpha on xn can be evaluated recursively. So whenever we find a recursion, that is what we need in dynamic programming. Because we are somehow, this is the trick in this chapter, the only trick that you need to know. Because we are very smartly relating mu of alpha to mu of alpha xn minus 1. So we are relating two different nodes, and so this is the only potential that you need to multiply. And of course you marginalize over that variable. So this is how, because in dynamic programming, the only thing that you need to know is just finding a recursion, how the n could be related to n minus 1, so that everything becomes just a ladder, like from one go, it's like inductive, it's like an induction. And then because you need the mu of alpha, you just sum over the potentials and sum over x1. And of course, passing messages around the graph for mu beta, the same thing. It can relate mu of beta of xn to mu beta of xn plus 1, and this is really important. And this recursive message passing is shown here. I will show you the factor graphs. So factor graphs, as I said, you have simple node, then you have factor, then you have simple node. So no two simple nodes are connected to each other, so this is wrong. And no two factors are related, so this is wrong. So whenever there is a node, it should be connected to factors. And whenever there is a factor node, it should be connected to simple nodes. And so we multiply these factors to get the probability of X. This is an example of factor graph which corresponds to this factorization. You see, first, this click FA of X1 and X2, this one. Then you multiply FB of X1 and X2. Then you because they are independent, but multiply FC of X2 and X3. Then we multiply X3 because that's the only thing that's remaining. So if you multiply, then you want to maximize this probability. So for example, if you have a label on here, you want to maximize the neighbor label because you have training data. For example, in natural language processing. So factor graphs, these are simple examples of factor graphs. And this is event extraction. What is I like? Because now we are decomposing the problem of event extraction that I have explained my playlist for event extraction into this factor graph. It's very general. Because we are not, for example, here we are not learning these entities alone, just using simple conditional random field. We are learning it jointly because loss of the entity is summed by you add the loss of the event relation and also within event relations. So you learn all of them jointly. So your total loss in event extraction, that article in 2016 from Carnegie Mellon University is really beautiful. And they learned that they did the inference with the sum product network, sum product algorithm, which is just as we call it loopy belief propagation. So it's a kind of belief propagation. Or because Judell-Pearl, if you have seen the papers of Judell-Pearl, and I've explained his causality methods 2 years ago, you will notice that all of them are the same. Some people talk in the context of message passing, loopy belief propagation. Some people say in the context of sum product, but the basic idea is the same. You're passing the messages. And nowadays it has become very advanced that they combine graph neural networks with the inference of the idea of inference for these factor graphs, which is really amazing because you're combining the power of graph neural networks with that idea, the classical idea that we know from 1990. We combine these two ideas, so it becomes a very mature theory. And people in Stanford are working on that. In the next lecture, I will show how people in Stanford are taking advantage of this beautiful structure.